begin to summarize the galvanic cell on page 6 of your lecture notes. You should have aluminum being in the anode and the nickel being in the cathode. We would need aluminum then as the electrode and nickel as electrode, and in solution we have to have the ions. The electrons flow from the anode to the cathode. The salt bridge is in there with a very soluble salt. The purpose is to replenish the charge that builds up. And the anion always goes to the anode and the cation goes to the cathode. And an equilibrium expression for this reaction would be the concentration of the aluminum ion squared over the concentration of nickel ion cubed. All right? Sometimes in these drawings, you know where we have a V, because that's what we'll be doing, is we'll be measuring the voltage that is generated. But right there, they'll make little squiggly lines, and it's called the load, because that is where you could actually put something that you want to use the energy for, like a light bulb or whatever. So you can see some squiggly lines there, or you can see a voltmeter or something like that. Okay, so that is our introduction to a galvanic cell. Now some miscellaneous points of a galvanic cell.
So when the salt bridge is gone, so the reaction would slow down and come to a halt after the salt bridge is gone?
Yeah. But that gel, there's so much, and when you think of it's going on atom at a time, that usually is not an issue. Okay, particulate level drawings are very important, a new emphasis on the exam, and they want you to show what would be going on at the particulate level of those electrodes and the impact it would have on the mass. All right, so let's look at the one we just did on page 6. And if we solve this at the particulate level, we have these neutral aluminum atoms that are the electrodes, correct? And this would be the particulate level, the little atoms. Okay, and they are being converted into aluminum plus 3 ions, aren't they? So what is happening to the mass of the anode? Very good. Okay, so the mass of the anode is decreasing. All right. Now, just a, preview of coming concepts. They'll do this with Le Chatelier, and they'll say, what will happen if you have a bigger anode? Would it do anything for the overall voltage? No, because that equilibrium expression doesn't include solids. Okay, so that's kind of a trick question. The size of the anode is irrelevant to the flow that we'll see from a Le Chatelier later on. Okay, remember, yes, the mass will change. Yes, you need to show which direction the mass will change. You don't just say the mass will change, right? Too vague. All right, you need to show the particulate level why that mass would change. But does it affect the equilibrium or the overall voltage generated, the size? No, because solids aren't involved in the equilibrium expression. We're going to be tying the equilibrium expression to voltage. And so it's important to know what would and wouldn't affect that in the overall cell. But we'll get to that later. Like I said, I'm just introducing it now so that when we see it, it's not completely new. All right. Meanwhile, over at the cathode, we have neutral nickel atoms that comprise the electrode, correct? And what's happening is the nickel ions are being converted into nickel atoms, right? Nickel ions are being converted to nickel atoms. Okay, So what's happening on the cathode?
As it's increasing.
Yeah, mass is increasing. All right, and what's happening then is these electrons are going this way, right? And then the electrons then are going here, aren't they? So we see that full circuit of what's happening to the electrons. They're being generated by aluminum losing them, and the nickel is taking them in and being converted into nickel atoms. And, you know, once again, see this for the video, see that? But look at all that silver that's plating out, okay? That would be the equivalent of what's going on the cathode, is all that silver building up. But because that silver is building up, what's happening to the size of the copper wire? It's getting smaller, and it's building up.
Looks like a caterpillar.
Yeah, it does. So it looks like, actually looks like tinsel. All right. Okay, so it is important that you be able to know what is going on the particulate level of the anode and cathode, right? To explain what's the impact of the mass, and to be able to show, you know, what's happening to the electrons so we can see that transfer. What's the result of this transfer? And the result is these neutral atoms are getting ionized, and these ions are getting neutralized, so to speak. Okay, we can have inert electrodes. Electrodes that are not involved in the reaction at all. As you can see in the previous two examples we've used in this lecture, the electrodes were part of the reaction. They were the metal, right? But what is common is sometimes you can have a half reaction that is an ion just getting further oxidized. You don't have a metal, right? And what you would use in that case is what's called an inert electrode, and it's usually made of platinum or carbon, unreactive elements. And all they do is serve as a conduit of those electrons. So their mass is never affected. Right? What's going on is in solution. And then the electrons, you know, glom onto that electrode and are pulled over. So if the electrode is inert, then its mass doesn't change. Right? Because nothing is happening to it. It is just, you know, helping the electrons along. It's taking them from solution and pushing them over. Just acting like a bridge. Okay? So we can have inert, and the general ones used are platinum or carbon, and they're usually shown by drawing it really thin. When we have electrodes like this, you know, we know that's metal. That's just how they usually show it. If it's just an inert, they'll just show it as a line. Okay? We can also have gases that are involved in redox reactions. The most common one is hydrogen, because hydrogen will be oxidized to an H+. It looks a little different, okay? And I just want to show you how it's drawn. You've got an inverted tube, right? That is attached to the source of the gas. So a hydrogen tank, whatever. And then that gas, and we'll say hydrogen, is, you've got this half cell, right? Right, and then you've got an inert electrode there. So I've got this inverted tube so that the gas doesn't go away. In solution then is an ion that matches that. So it's usually an acid, like hydrochloric acid. Why would we want a strong acid? Yes. We want to keep that nice source of H+. Okay, so the half reaction is, you know, H+ going to, okay, Okay, that's the oxidation. All right, but we have to set it up differently, obviously, because it is a gas. We put an inert electrode, and then the electrons generated by that go up that inert electrode and go over to the cathode. So the classic galvanic cell is the one that I showed you in the first two examples where we have the metals. All right. We can, if we have situations where we don't need metal, have an inert electrode. An inert electrode is also important when we have a gas. Right? And with a gas, we have to have an inverted. Okay, that is lesson 3. We'll stop here. In lesson 4, we'll find out why the electrons move and how much electricity is actually generated by that movement. So qualitative, and next lesson is quantitative.